this closely to the original software implementation, but most of the time this is much more complex. Now, actually, may I point out that the code that Hastlayer generates is commented. These green things here are comments, and also formatted, as you can see here. So it's probably already writing better code than some of your colleagues. But let's go back to the slide deck again, and let's see what's in for Hastlayer next, because this is the state of the project, but we are, of course, not stopping here. For example, we have engaged into a partnership with the Wigner Research Center for Physics, which is part of the Hungarian Academy of Sciences. And those guys are pretty smart, mostly physicists. For example, they also work with CERN, you know, the institute that also has the Large Hadron Collider. And the Large Hadron Collider's data is actually fed to two data centers, and one of those data centers is at Wigner too. And what we are doing with them is that we are checking how Hastlayer can potentially accelerate scientific computations, because obviously scientists have a lot of numbers to compute and not a lot of numbers to crunch. So tools like Hastlayer may be useful there. And the first thing that we are working on is something called 3D KPZ surface growth simulation. This is a quite curious algorithm. It's basically an algorithm that can predict how the surface of a material can change over time. So, for example, if you have a chip wafer, a silicon wafer that is used in chip manufacturing, then this algorithm will be able to predict how the surface of that wafer can get new imperfections or issues. We will see how this will be implemented with Hastlayer. We are working on an implementation, and once we have that, we will be able to compare that with their existing GPU implementation. We are also working on floating point, because actually floating point numbers are not supported with Hastlayer yet, and this is actually what FPGAs generally struggle with. And since we are working on floating point, we also sought to go a step further and check out some new number types called unums and posits. The unums and posits were invented by a mathematician called John Gustafson, Dr. John Gustafson, who also worked at AMD before. And what these two number types that are also floating point number types promise is to be better, have a better range and or accuracy with the same amount of bits than the IEEE floating standards that we all use. So instead of floats and doubles, as in .NET, you would be able to use posits with Hastlayer, for example, although they will work from a developer point of view very similarly. They will offer better answers. And we have already created a unum proof of concept that is also possible to transform into hardware. It also works on the FPGA, so we kind of have a unum processor already. And this is kind of cool because you can even create your own number type. And with Hastlayer, after you create the .NET library, you can create the hardware implementation within seconds as well. But there's more. We are working on more use cases to field test the system to see how it can be improved. And we are also making Hastlayer high performance computing ready. As mentioned, what we currently only support is this low-end, slow and small FPGA. That can be used for evaluation, but which is not really useful for production workloads. We are working on supporting bigger and faster FPGAs to allow that. And it seems that FPGAs are also coming into the data centers. So AWS, the Amazon Cloud, already offers FPGAs. There are virtual machines with FPGAs built in. Azure, as mentioned, already has FPGAs too, although they are not yet publicly available. I would guess that they soon will be. And Intel is betting on FPGAs as well. Intel acquired the second largest FPGA manufacturer called Altera about 2 years ago, and now Intel is an FPGA manufacturer. And they are working, among others, on bringing together CPUs and FPGAs. So particularly, they have built a Xeon processor that is packaged together with an FPGA, and they are also working on eventually bringing them together on the same chip. And if you think about it, looking at FPGAs as a CPU manufacturer is quite logical, because with CPUs we are hitting boundaries again. CPUs have reached their architectural limits of efficiency a long time ago, more or less. The clock frequencies can't be higher anymore. And we are now also reaching the physical limits on how many transistors can be packaged on the same chip or on the same die. So there can't be more cores anymore either. So we need some way to make CPUs much faster, but without actually bumping into these physical limits. And FPGAs are a way around that, because if you put an FPGA into a CPU, you can basically offer an application-specific CPU core, or even more of them. And that way, you can make applications run faster without actually making the CPU faster. So let's wrap up. If you like this, and I really hope you did, check out the SDK on GitHub. It's up there. And be ready, because FPGAs are coming. As mentioned, they are already in data centers, and eventually they will be as accessible as GPUs today. Because if you can remember, a few years ago, GPUs were kind of a curiosity as well. But slowly, they became more and more accessible for everyday software developers, and now they offer pretty convenient APIs. The same shift is happening with FPGAs too, just much faster since we are in a more modern time. Though FPGAs are still kind of a bit the curiosity of specialists, but very soon they will be another kind of computing device that pretty much every software developer can utilize. So that's all, folks. Thank you very much for your attention. If you have any suitable performance-intensive .NET program or any other software that you think would be a good use case for Hastlayer, get in touch with me. I would be happy to talk about that with you. Otherwise, Hastlayer.com is the project homepage. As mentioned, the SDK is up on GitHub. And if you would like to hear more about the people at Lombic, check out lombic.com. And now I would be happy to have a bit of conversation if you have any questions or remarks.
Zoltán, yeah, leave that up there. The details about everything. Thank you very much. By the way, I totally screwed it up at the beginning. You know, we are .NET FLA, and there was a recruiter if you guys want to talk to them. And thank you, Zoltán, for taking care of drinks and carrying and a fantastic presentation. You can get a lot of photos from us. And do you have any questions from the experts here? Let us know if you can't hear.
Hey, Zoltán, can you hear me?
Yes, I can hear you. Hello.
That was awesome. That was really cool. Question for you. Have you looked at whether this thing could make a lot of money sort of mining crypto altcoins? Because you can adapt the algorithm really fast to a sort of hardware implementation. Is it going to be efficient versus a GPU type implementation?
Very good question. Thank you. The short answer is that maybe yes. We haven't tried that, but it's quite interesting because as you already mentioned, more or less GPUs are the tools used to mine pretty much everything apart from Bitcoin. With Bitcoin, ASICs, so application-specific integrated circuits, so basically hardwired chips became feasible a long time ago. So Bitcoin is now mined only with ASICs, but for all the other cryptocurrencies, GPU mining is the most dominant. And indeed, FPGAs do have a role there. FPGAs were used for Bitcoin mining. I have read about somebody trying FPGA mining with Ether, I think, and Zcash, probably also Monero. And it would be really interesting to see how FPGAs compete with GPUs, because the big issue with mining is that it's not that it takes a lot of time, but it takes a lot of power to get some substantial cash out of it. And since FPGAs are really power efficient, much more than GPUs, they can have a quite big advantage there potentially. But there are not many FPGA implementations yet, probably because FPGA development is quite hard. So with Hastlayer, it will be possible to implement an Ether miner or something like that. Somebody else actually also inquired about that, and I think they are testing Hastlayer for that matter as well.
What kind of limitations in terms of the subset of C# or the .NET framework are you working within when you're using Hastlayer? I mean, for instance, I noticed you have you had a constant defined for the level of parallelism. I assume if that was, I couldn't figure it out to do the FPGA generation. So, what do you have to keep when you're actually coding for Hastlayer?
Yeah, that's quite observant. Indeed, we have a constant for how many tasks there will be. And basically, the short answer is that since we won't run that code on a CPU that can dynamically fetch anything from the memory, but rather we will hardwire kind of all of this logic onto a chip, you can't use some kind of dynamisms. For example, the level of parallelism you have should be compile time defined, basically the number of tasks, because that many instances will be wired onto the FPGA, so that can't be dynamic. Also, if you are using arrays, you have to statically define the size of the arrays as well, because basically on the hardware you will get a series of registers or something like this, and obviously it's only possible to implement that on a hardware if you know how many of them there will be. That being said, you still have the onboard memory there, that simple memory that I've shown, that can be used for dynamic memory allocations, and also for object-oriented code, so where you are instantiating classes, this doesn't limit you too much. Because theory, for example, you can have a loop where you instantiate a class, and it will work, because what you are doing here can still be hardwired, but you can't have a dynamic linked list, for example, just there without some simple memory interactions. What you can do with Hastlayer is actually documented on the SDK in detail. So much more details there than I can tell you here. And also there are many more samples that showcase what is possible with Hastlayer. And actually, one interesting thing that the aim of Hastlayer is to support as much of C# and as much of .NET, because again we are using the decompiled code as possible, and to offer you a developer experience where you can't really notice Hastlayer. And because of that, even the pieces of the .NET framework can be transformed. So where obviously nobody knew about Hastlayer. I particularly tried methods of the math class as a test, and and those can be transformed as well. Sorry, now I can't hear you.
When you said it's an alpha product, what's alpha about the platform and what's reliable?
Mm-hmm. What's really reliable, as it seems now, is the transformation logic. So the logic that you will get once Hastlayer finishes will be pretty much correct and will provide the same results than in .NET. So we are pretty much confident in that, although it's surely not perfect. What makes it alpha is that we only support this small and slow FPGA board. So with FPGA development, it's quite different than with programs. You can't really have a multi-platform FPGA design. There are ways around that, but long story short, it takes a lot of time for us to support another FPGA. So what we are working on is supporting a bigger FPGAs, and with that we would be able to offer much more performance and much faster communication with the host PC via PCI Express, for example. And once that is done, we will be out of alpha, because at then you won't be able to just evaluate Hastlayer and to test it with samples or reused real-world applications, but rather you would be able to just push real-life workloads on it.
Thank you.
Sure, thank you for the questions.
I have a couple of questions. If you guys have some questions, just let me know. Just FPGAs to me are fairly. I'm here. Oh, fairly new. So please excuse me. So what I didn't understand. I mean, just the basics. It's saved. The moment you disconnect it, you're not losing any of the code, as you would say from an Arduino. It's constantly running there. The moment you turn it on, it's there waiting for the request from the .NET on your PC. Is that correct?
It can be. Okay. Basically, just to give you a bit of an insight, when you are programming an FPGA, you kind of load the hardware configuration onto the chip, and while the FPGA is on power, it will stay there. And configuring an FPGA once the hardware design is actually prepared takes about 1-2 seconds. So that's not nothing too much. But when you switch power off, that design from the FPGA chip will vanish, and you have to reprogram it. So again, 1-2 seconds. That being said, there is also an option to use an onboard ROM or flash memory of the FPGA board that will allow what you mentioned. So once it powers up, it immediately has the configuration prepared as well, and it can immediately listen to inputs.
Yeah, I mean, essentially, if we wanted to do what our friend here wanted to do, is create like you said, Zcash, Monero, whatever miner, you could do it and without the PC, because they would load from the EEPROM. Is that what you said?
Pretty much yes, or formulate otherwise. What would be possible to do is that you could have an FPGA cluster, like dozens of FPGAs hooked up to an Ethernet network, and since the configuration with a flip of a switch you could push into the flash memory, then that means that even if you have a power surge, once power goes up, the FPGAs would be able to work again without any further ado. Also, let me touch on something else, another part of your question or aspect. What we currently support, the model of using FPGAs is that we have a host PC, and the FPGA is kind of an accelerator, like a GPU even. That means that we are not supporting, well, it's possible to implement, but we are not explicitly supporting scenarios where you configure an FPGA with Hastlayer, you put it somewhere completely independent of a host PC, and it just works on its own. The idea is to always have a host PC somewhere, even if it's remotely, even if it's a single host PC for dozens of FPGAs, that that distributes some work and pushes that onto the FPGAs.
And you mentioned that the network stack is in there, so that communication could be done over the Ethernet, right? Not only by the USB.
That's right. That's actually TCP/IP, so not just the physical level, but also that level.
Right.
So yes.
Okay. Thank you very much. We have one more question. Yeah?
Thank you.
Sorry ahead of time if it's already been answered. I just came right from the airport. Was late.
Sure. No.
So my question is regarding security. So if I have proprietary data, and algorithms that I don't want someone to copy, can I obfuscate the code on the FPGA so people can't reverse engineer my secret algorithm?
Mm-hmm. Thank you. That's also a very good question.
To give you more specifics, basically Python script type stuff to input output, but my IP is the actual script itself. It's simple scripts, but it's how I do it.
Mm-hmm. Well, first of all, the .NET assembly itself can be obfuscated. So what is processed by Hastlayer can already be an obfuscated algorithm, so the output will be comparably obfuscated too. So if you are worried about somebody reverse engineering your algorithm from the hardware code, that could be one of the solutions. Also, if you are distributing the FPGAs or the already prepared hardware designs to your users or your clients, then you can also basically encrypt this hardware component that Hastlayer generates too. So you can say that, hello customers, you can get a hardware accelerator card for my algorithm that, by the way, I have developed with Hastlayer, but you don't have to know about that. So here it is. You can purchase this card that is pre-programmed, pre-configured for you. And even if they are hardware engineers, they won't be able to
type thing?
Get. Sorry?
You mean like a smart card that only has a certain number of uses?
A smart card.
You said card, right?
Sorry?
Because you said card. I'm asking. So do you talk about the smart card concept?
Sorry, I should have rather used the word board. So FPGA boards that you can plug into your PC, for example. But smart cards won't work with FPGAs. So smart cards are very small, and FPGAs are much more bigger than what can fit on a smart card. So with smart card, that's too small. But FPGA boards can also be much smaller than the one I have shown you, because there are all these bells and whistles of a development board that you don't actually need.
So, question, what would you see as the speed difference between doing a custom ASIC versus just doing a Hastlayer with the FPGA?
Mm-hmm. Basically, remember the charts that I've shown with the different merits of the different devices. ASICs would be something where all of the merits of FPGAs are exaggerated. So with ASICs, you can get an even bigger level of parallelism with the same amount of silicon. It can be even more power efficient. But the difference is that it will be much more expensive to create. Because with an FPGA, you need to buy an FPGA. That can be a couple hundreds of dollars, sometimes a couple thousands. And then you need Hastlayer, and bringing the two together, you will just write your .NET code and get the hardware implementation. With ASICs, however, you also have to manufacture them. And now, actually, the hardware code that Hastlayer generates could theoretically, after some transformations, be also used for ASIC manufacturing. You need a couple $1 million to do that, because ASIC development is very expensive. You also need a lot of other stuff apart from what Hastlayer generates. You need engineering to verify that a lot before actually manufacturing it. And then manufacturing it takes a lot of money as well. But ASICs are, just as on the example of Bitcoin mining, are feasible if you want to get well, the maximum performance and power efficiency, and secondly, if you can solve tens of thousands of units. Because if that is there, then the millions of dollars of investment will be returned, and then after you are manufacturing your ASIC, it will be cheaper to manufacture per piece than having an FPGA configured.
Thanks, Zoltán. I'm fascinated with this. So if I want to get my hands on, and correct me if I'm wrong, at this moment, there's only that one board that's supported, or is it a family of boards? Is there more than one, or just the one?
Mm-hmm. Yeah, thanks for that question as well, Damien. This is just this particular board now, unfortunately. We are working on something having better and even easier to test even, but right now this is just this board. Where you can buy it is also linked from the documentation of the SDK. This is not something that we created. We just selected a development board out there. This is just that.
Okay, and that's fine. And where do you suggest, if we want to get into this, to purchase this board? Where you had some icons from SparkFun, which is a big supplier here in the United States. Do they have that board? Do you know of if they do, or do you have a suggestion where to purchase it?
Yes, yes. The web shop where you can also buy it in the US is also linked from the SDK, but it's actually manufactured by a company called Digiland. And Digiland is a partner of Xilinx, the FPGA manufacturer. So they buy FPGAs from Xilinx and put them into boards. And Digiland is a US company. They also have local distributors all over the US. So I would imagine there should be some local distributor pretty close to your location as well.
Awesome. Anybody else have any questions? No? Zoltán, that was amazing. Thank you very much. And thank you from all of us. Thank you. One time. Oh, okay. Oh. No problem. No problem. Zoltán, they want us to. We have this our master photographer, and he wants to show everybody that you were kind of here with us. Is there a way to put you on full screen?
Yeah, sure. Let me stop screen sharing.
Great.
You should see me full screen now, I think.
There we go. All right. Do I look like I'm next to Mr. Zoltán? Famous guy, you know. So I gotta go. You're us. Thank you so much, my friend.
Thank you very much, guys.
This, right?
Have a nice remaining meetup.
Excellent. Oh, thank you. Thank you so much, and we'll see you next time. Thanks a lot. Next time you got to come here.
Oh yeah, I will definitely visit Florida one time.
So you're very welcome. You'll find this very, very great place to do that. Make sure to if you do, make sure to look me up. I'll show you all the best places around here. Okay?
Oh,
I promise.
Thank you very much.
Thank you, Zoltán.
Bye, guys.